This is the review video over Chapter 20, Electrochemistry. I'm going to do one free response question as well, so turn to page roughly 3, I think. We'll do number 12 together. So we have a diagram showing a galvanic cell. We call this a voltaic cell in the notes. Same thing, voltaic, galvanic, but you recognize two compartments, electrochemistry going on. Notice we have a reaction. We have aluminum becoming aluminum 3+. We have zinc 2+ becoming zinc. Right away, notice that aluminum is being oxidized. Zinc is being reduced. So it's important to recognize that at the outset. We're assuming the temp is 25, which is usually the case. And let's answer some questions. The diagram includes a salt bridge. Here is the salt bridge. You have to have a salt bridge in order for the electrochemical cell to work. With a saturated solution of KNO3, describe what happens in the salt bridge as the cell operates. Now, in the left compartment, we have aluminum. We said aluminum is being oxidized. So right here, aluminum is actually going into the solution from Al to Al3+. And as that happens, electrons are produced. Oxidation produces electrons. And then electrons go this way. So the electrons travel from the left to the right. And the aluminum then produces a bunch of plus charge. So we're increasing the amount of pluses in this left container as oxidation is taking place. We must counterbalance that by moving nitrate anions into the left compartment. The salt bridge puts the negative ions in here to remove the positive or to neutralize the positive. So we can say that NO3 minus moves into aluminum half cell. We can call these half cells. And then the same thing happens here. As the electrons come in, the zinc takes up the electrons and plates onto the electrode there. So we're actually losing positives. So we have to replenish the positives by putting potassium ion in there. So K plus would then move into zinc half cell. You can call it zinc 2+ half cell. I probably should have said aluminum +3 half cell, like that. Good. Make sure you understand how the electrons flow. Make sure you understand how the salt bridge flows. Now, real quick, aluminum will be losing mass. So we're actually eating away at aluminum here as the cell operates because we have to remove aluminum. We're putting aluminum into the solution, essentially. On the contrary, on the right side, the zinc half cell is actually getting heavier and heavier and heavier. That's the idea. Good. The next question asks us, determine the value of the standard voltage for the cell. Now, that would be, remember, just kind of like thermodynamics, the whole voltage is products minus reactants. In our case, we said let's do the cathode minus the anode. Now, this is oxidation, so we call this the anode. This was reduction, so we call it the cathode. Remember how we designated that? C with reduction, the consonants and the vowels match up. So the electrons are going from the anode always to the cathode. Very important to remember. So it's like we're doing products minus reactants. We're doing the final minus the initial. Final destination of the electrons minus the initial. Cathode minus anode. Now this equation is in the equation sheet. However, the reduction potentials for the cells, I went ahead and attached at the very end. If we take a look at the very end, a page for the reduction potentials. Now, the reduction potentials are, so on page 3, possibly. Right, so I actually have it in a separate file. But take a look at page 3 and find, if you could find zinc and aluminum, you will probably recognize that aluminum's, so go ahead to the back, and you'll find that aluminum's reduction potential on the very back and zinc's reduction potential are listed. So zinc and aluminum are actually pretty close toward the bottom, and zinc should be slightly, aluminum rather wants to get oxidized, zinc wants to get reduced, so zinc's should be slightly larger than aluminum's. So if you take a look, zinc's reduction potential should be -0.76. Aluminum's reduction potential should be -1.66. Notice zinc wants to get reduced more. Remember, the higher the number, the more the element wants to get reduced. This number is higher than this number. So we'll do cathode minus anode. Our cathode, again, is zinc. Notice zinc. So we'll do -0.76 minus -1.66. So we have to subtract a negative. In this case, we end up adding a positive for a total of 1.66. Apologize here. 0.9. I could have done that. Not looking at the notes. 0.9. All right, that'll work. Good. And then they're asking us about delta G. So they're connecting delta G to the electrochemistry. Now, anytime the voltage is positive, the reaction will run on its own. And remember, when reaction runs on its own, delta G turns out to be negative. There's an equation they also give you that looks like this. Delta G equals negative NFE. F is a constant, N is just the number of moles. So you take the voltage, which is E, you put a negative on it, and that's how you get the delta G. So whenever voltage is positive, then delta G ends up being negative. So we should say the value, indicate whether the value would be positive. So we'll say positive because E cell, no, we shouldn't say positive. We should say negative. Apologize. I'm a bit of a mess here. So we should say negative because E cell is positive. And then you can say via the equation, then you can go ahead and show delta G is negative and FE. We can do that. This should be a sufficient explanation. The last part, part D, asks us about something about the concentrations. Now, if you take a look, the equation itself, or the cell itself, has 1 mole of concentrations. This is why we're under standard conditions. Remember, one of the requirements of standard conditions are 25 degrees Celsius, 1 atm, as well as 1.0 molar solutions. So both these are standard. Now they're asking us, well, what if our aluminum cell is lowered to 1.0? From 1.0, I'm sorry, to 0.01, so 100-fold. We're decreasing it by 100-fold. Well, there's an equation that says E is E naught minus, we got a constant 0.0592 divided by N times log of Q. And the idea here is that the standard at 1 molarity concentration gets reduced by this factor right here, and it's really log of Q that affects it, and then we'll get the non-standard conditions. This is essentially when the battery starts running, your voltage starts changing, and this can calculate what it's at. Now Q, remember, is the reaction quotient from equilibrium. It's products over reactants. Our products over reactants used to be 1. It used to be 1 over 1. 1 over 1, log of 1 is 0, so this whole thing would cancel out, and these two would be the same whenever the reactions are 1 and 1. If they're not, in this case, we're making the product, let's see, we're making the reactant, the aluminum half cell. We're getting this guy right here, our aluminum half cell. Aluminum actually was getting oxidized, so our product, aluminum's our product is going to decrease. So now we got 0.01 over 1. Now, if you take the log of this, so this would be 0.01 here. If you take the log of 0.01, you'll actually get -2 for the answer. That's because this is 10 to the negative second. And we got a negative number, which multiplies by this negative number, and we end up adding. I know that may have been a bit confusing, but see if you can think through it. So we've added a number, and our voltage actually goes up. So we would actually say increase. And I would justify the answer by showing either this, or you can also say, since we're adding product, the voltage will go up. Whenever you're adding a reactant, well, you probably have to show them using this calculation. So our voltage will go up because of the Q. Q would decrease. Log of Q will be -2. Hopefully that makes sense. If this one doesn't make sense, think through it. And let's do the last one here. Number 13. This will be a short one, but still. We have a fuel cell that uses chemical energy to produce or stored energy to produce some electrical energy, and it's based on the table on the right. So we have 2 half reactions here. Write the equation for the overall cell reaction. Now, if you take a look, this one right here has a higher number. This will be reduced. This will be oxidized. So this will be reduced. This will be oxidized. So we'll actually flip this one. So we'll have to flip. We'll also have to make sure the electrons match up. Notice this has 2 electrons. This has 4 electrons. So anytime we balance an equation, remember the electrons allow us to balance it. So we have to make sure that both of these match up. So as we flip it, I'm going to double this whole entire reaction. We have 2 to 4, got 4 OH minuses, plus 2 H2, giving me 2 H2O, 4 H2O rather, 4 H2O, and 4 electrons. Right, so this reaction is now out. Now you don't have to do anything to the number because this is different from delta H. These are actually intensive numbers. So, or our equation, cathode minus anode, will just be the reduction potentials of the cathode minus the reduction potentials. These are reduction potentials, so you still do use those numbers. If you don't, if that doesn't make sense, just memorize that. So now what we have is we have 4 OH cancel out. These are out. We have 4 electrons. Obviously, those cancel out. That was the whole point. And then we have a hydrogen plus oxygen of 2 waters. So we do have 2 waters. Cancel out right here. 2 waters cancel out, and we're left with 2 waters here. Excellent. That balances the equation. Now, if we clean it up and rewrite it, we have this, this, and we have this left over, which actually makes a pretty simple reaction. So we have oxygen plus hydrogen giving us water. And there's 2 waters because there are 2 hydrogens. So this is actually the balanced equation. Very simple balanced equation. Hydrogen plus oxygen gives us water. Not bad? To get the standard cell potential, we'll do cathode minus anode. Our cathode, we said, was 0.40 minus our anode, which is negative 0.83, giving us a total value of 1.23 volts. Notice I didn't flip this number because we're doing the reduction potentials of the cathode minus the reduction potential of the anode. That's an important little piece. All right, how about a quick little stoichiometry with this? We have 0.93 moles of H2 that's consumed as the cell operates for 600 seconds. Calculate the number of moles of electrons that pass through the cell. This is the idea of amperes and so forth. So if you have 0.93 moles of hydrogen, they want us to convert to moles of electrons. And the number of moles of electrons is actually going to be 4. So we'll actually use this number right here as 4. You could have also gotten 4 by looking at oxygen. On the left side, we have a charge of 0. On the right side, we have 2 oxygens, total of negative 4. We must have gained 4 electrons. If you analyze hydrogen, you get the same idea. So we have for every 2 moles of hydrogen, we're actually requiring 4 moles of electrons. Not bad? So we're essentially doubling that number, and we got 1.9 to be true to significant figures, moles of electrons. Lastly, they want us to get the amps. Now, the amps are actually related to Faraday's constant. Faraday's constant, remember, says that 1 mole of an electron equals 96,500 coulombs. And an amp, that's what they're asking us for, is coulombs per second. So we'll take the number from upstairs, which was 1.9 moles of electrons. Since 1 mole of electrons gives you 96,500 coulombs, you can get yourself a number that's like 179,500 or so coulombs. And since we want amperage is coulombs per second, and this is actually also given to you on the equation, we'll do divided by our seconds. We have 600 seconds. Divide this by 600, and we should get a fine value of 299 amps. Because we're working with 2 sig figs, this is actually going to be 3.0 times 10 to the second amps. We have to express it using scientific notation to express that idea. Good. So a little bit of stoichiometry with electrochemistry, as always. I'll work through some of the other questions. There are some questions in the multiple choice that do this same thing and practice this same thing backwards. So come with your questions to class, and we'll see you there.